the fifth and last lecture on naturalness. Today, well, we're gonna first complete what we started talking about some ideas to explain the Higgs mass in the multiverse, but also of landscapes that are not multiverses, because you might have noticed that all the ideas that we've talked about so far just rely on the fact that you have many realizations of the Higgs mass or the cosmological constant. They're not tied to having an actual multiverse where these realizations exist as causally disconnected patches in the cosmos. After that, we're going to wrap up this multiverse/landscape part of the course and try to summarize what we learned with a focus on potential signatures, the traditional answer that you will find if you ask whether you can see a multiverse explanation of the cosmological constant or the Higgs boson mass is no, but we will see that this is not entirely true. So there are some, but a large class of these ideas, which is the one that I consider maybe the most robust, does have signatures. After that, we're gonna make a bigger summary, so trying to recap what we learned so far on possible solutions to the cosmological constant and the Higgs mass quickly. And finally, we will conclude with some more exotic ideas, let's say. So some examples of UV-IR mixing, and maybe if we have time, also some examples of generalized symmetries that could explain the Higgs mass. So in both cases, these are ideas that, as they are today, do not work at all, but they suggest something interesting for future speculation. All right, so let me start with this, let's say, what I want to call statistical selection of the Higgs mass in the multiverse. So far we've seen examples where the Higgs mass was seen as small by observers just for anthropic reasons. So it's accidentally small because of a cancellation, and we see this unlikely universe because it's the only one where observers can arise. Or we've also seen cases where that I would call dynamical, where the Higgs mass affects the evolution of the universe by affecting the cosmological constant. So that was the example that I called crunching. But there is also another option, which is making a small Higgs mass very likely in the multiverse. And the simplest possible way to do that consists in adding our usual field strength of a free form. So for those that weren't there last time, I'm going to write the action again without explaining it too much. So this is the kinetic term of the tree form in analogy with the vector potential in electromagnetism. We've seen last time that these objects are non-dynamical in 4 dimensions, so they have a big gauge symmetry. So if you add any antisymmetric function with 2 indices, so the exterior derivative of an antisymmetric function with 2 indices, this remains invariant, and as a consequence, there are no propagating degrees of freedom for our tree form, and the only solution of the equations of motion for the electric field, so this F, is a constant times the completely antisymmetric tensor if you don't have sources. So if this is your action. Of course, I mean, we can add gravity as usual. Now I'm going to imagine that this object couples also to the X via some higher dimensional operator. So let's say that the natural value of the Higgs mass is around m Planck, but it starts off negative. Then, as we've seen last time, if there are charged objects, so branes that can couple to this tree form, just like point particles coupled to the vector potential with one index. Then let's say you start in a configuration. So as I was saying, the only solution of the equations of motion is something like this. So you can think of it as a constant electric field in your space of strength C. And just as in the same way as a constant electric field, if it's big enough, it can discharge by creating electron-positive pairs. This electric field can discharge by nucleating bubbles made of a brane and an anti-brane of opposite charges. This can happen if, for example, you have some interaction with a brane of this form. Where C are the coordinates on the brane surface. And I'm not going to tell you more than just writing it down, because we've already seen last time in quite a bit of detail, at least heuristically, how these terms are arising. And last time, if you remember, we used this trick to scan the cosmological constant. And then I just mentioned that one could do the same for the X mass by adding a coupling such as this one. But now there is more. So now I'm imagining that the charge of these branes depends on the X web. One example could be adding a second X doublet and a ZN symmetry, so that the only coupling that's allowed is something like this. Let me just check that I didn't mess up anything, but I think it should be fine. Yeah, so why am I adding this GN and this coupling? Well, the reason is that in this case, once you nucleate a brane, the X web is not changing uniformly at every nucleation, but is changing every time in a specific way. So imagine, for example, that I built my theory in such a way that the vacuum expectation value of this operator, modulo order 1 numbers, is proportional to the vacuum expectation value of the lightest X boson, that is CP even, so our X boson. And we're going to comment on how to do this later. So now I have a charge of the brane that depends on the X vacuum expectation value. And so you can ask, what is the change in X web every time you nucleate a brane? So again, we are in the situation of last time, where you start with a large positive cosmological constant. So you can add a bare one here if you want. You can add also the Einstein-Hilbert action. Okay, it's not crucial for our discussion, but let's say we start in the sitter. And so you will start in some patch with a large cosmological constant that will inflate. Then at some point, through this coupling, you can nucleate a bubble. In the bubble, the value of the cosmological constant is reduced, because if you plug in back the background value of the field, you're going to get that the effective cosmological constant is this. And just as in the picture of the multiverse that we've sketched a few lectures back, the inner bubble would like to eat up the whole space, but it's expanding only at the speed of light, while the space-time in both bubbles is expanding exponentially because of inflation, so they never catch up. And so eventually you have all these nested bubbles with different values of the cosmological constant, but in this case also different values of mx. And the interesting point about this idea is that if you ask how the X web is changing from bubble to bubble, it goes like check just to sure that I don't tell you anything wrong. So in this case, it's I mean, as the XVEV becomes smaller and smaller, you're nucleating more and more bubbles. And one simple way to see it is to compute that relative variation of the XVEV from a bubble to the next, which is, let me tell you in 1 second. Yes, I made a mess with the note, okay, which is just what I thought, so it's just this. So you see that if n is bigger than 2, as you go to smaller and smaller values of the XVEV, you're nucleating more and more bubbles. So if you want, like, if you plot the distribution of the bubbles as a function of the XVEV, initially you're moving by big jumps. But then these jumps are becoming smaller and smaller. And you have an exponential preference for being near 0. The problem is that this nucleation process is a semi-classical tunneling, and it's very slow. And so in practice, this model lives in eternal inflation. So it's impossible to compute the actual measure. So you can never calculate whether a smaller XVEV is actually more likely than a bigger XVEV. You might naively think that this is the case because of this mechanism, but there is no way to calculate it. And this is kind of a common problem of these ideas that try to make MH² preferred in the landscape. So as far as I know, all examples that exist, also beyond this one, live in eternal inflation, and they have no gauge invariant measure that they can use to really prove that the XVEV, that a small XVEV is populating most of the multiverse.
Sorry, I missed the what is n? Capital N?
N is a discrete number of your choosing, so you can
it's arbitrary.
Yes, you can imagine that you have a Zn symmetry.
Okay.
And so yeah, that's up to you.
Sorry, Raphael.
Yes.
There's a question on the model. Is this F mu F S squared H squared the only coupling you can write between these forms in H, or is
This one?
Yeah.
Well, I mean, in principle, you can have also higher dimensional operators, even higher dimensional operators. If you want to respect the gauge symmetry, I think this is the lowest dimensional one.
Even directly with A, like some.
Well, so A alone is not gauge invariant, you see. So if you look at it, you see that this is very similar to your usual electromagnetic Lagrangian. So this is the kinetic term, and this is the coupling to the equivalent of the current. And just like in electromagnetism, there isn't any other low-dimensional object that you can write down which is gauge invariant.
Like not in. Oh, yeah, okay. You have the kinetic term for the Higgs, where you could have it has a charge under this. I mean, for A, if it's just one vector potential, it would be the covariant derivative applied to H, and then its interaction with this A.
Well, yeah. Well, I see what you would like to do. So, but so first of all, so the object charged. So the only way. So as you can see here, the only way you can build a gauge invariant object is by coupling this vector potential to an extended object of three dimensions. If you try to write a covariant derivative with X, I think it will not work out. Yeah, so having said this, so this was just, let's say, to complete the picture of the three distinct ways in which you can select the X mass in the multiverse, which, I mean, I like to call statistical, anthropic, and dynamical. And in 20 minutes or so, we will go back this distinction and list the examples that we've seen last time under these labels. But I should say that these labels are arbitrary. I mean, these are a way that I find useful to think about these objects, but you will find people arguing with it. And the distinction is not really crucial, okay? I'm showing it to you because it's a useful mnemonic device. So statistical, we've just seen an example. Anthropic are these arguments based on the existence of observers. And dynamical, well, we haven't really seen yet an honest example of dynamical, because the crunching idea that I showed you last time was relying in some sense on an anthropic argument, because the same anthropic argument as for the cosmological constant. If you want to see a truly dynamical way, this is what's coming next. And incidentally, what's coming next is also an example of a landscape that is not a multiverse. Okay, actually two examples of landscapes that are not multiverses, and are known as the relaxation and then naturalness. And by the way, so I'm never citing papers explicitly during these lectures, but you will find all the references in the PDF. Okay. Also for the idea before. The idea before was one of the oldest ones, like IA, and well, you will find the references for the other ones in the notes. So let's start with the relaxation. The relaxation case, we are not imagining that there is a multiverse. For the moment, we're just imagining to couple the Higgs to some light scalar in this way. So we are implicitly imagining that, okay, there is the weak scale somewhere here, and then at some scale m squared, there is some symmetry, maybe supersymmetry or scale invariance, but the Higgs mass doesn't receive corrections above the scale m, so its natural value is m squared. And further, we are imagining that the scalar has a potential controlled by this small parameter g. So when g goes to 0, the scalar has a shift symmetry. And we will take this g coupling much smaller than the scale m, which is technically natural precisely because of this symmetry. And furthermore, we are also going to add some coupling of our scalar to our favorite operator in the standard model that we've already seen last time. So two antisymmetric contractions of a gluon field strength. So we're going to give it an axion-like coupling. You should already be slightly suspicious because I'm giving to phi a non-compact potential and at the same time a compact one. So you might worry that I'm mixing up things. I mean, in some sense, a field can either be a phase or not be a phase and not be both. And indeed, you will see that this is the main obstacle to you be completing this model. But for now, let me ignore this fact and just march on. So since G is much smaller than M, I can expand this part of the potential. And I'm going to imagine that G is so small that for all practical purposes, I'm going to see just the linear term in phi. If this is the case, the potential of the scalar looks like this. There is this tadpole, and then at some point, when phi becomes of order m over g, the Higgs boson gets a non-zero web. So maybe I got the sign wrong. Yeah. So at some point, when it becomes of order minus m over g, the Higgs mass squared becomes negative. And when the Higgs mass squared becomes negative, this, at least at zero temperature, let's imagine that we're at zero temperature, this term generates a potential for phi from the non-perturbative dynamics of QCD. We didn't really see in detail how this happens, but, and also today, I'm not sure that we're going to have the time. Let me just write down for you an approximate form of this potential. So this is an approximate form, but it highlights the fact that from the point of view of QCD, this phi is a phase or a Goldstone boson, if you prefer. And so if you add this term to the potential, you will find these oscillatory terms that become bigger and bigger, because as you keep going down, the mass of the Higgs boson is becoming more and more negative, so larger in absolute value and more negative. And so you see that if the scalar is moving around in the history of the universe, for instance, rolling down the potential, you are populating in time many different values of the Higgs mass. So this is a simple, very simple example of what I would call a landscape. So you have many different values of the Higgs mass that exist during the history of the universe, but it's not a multiverse. So in some sense, these values are in causal contact with each other. One comes after the other, and an observer might have seen multiple values of the Higgs mass in its lifetime. You already see also a second problem, which is that to really see this full span of the potential, I have to go to field excursions that are bigger than m over g. So I'm kind of breaking my effective theory. But let me imagine, again, let me be generous to the idea and say that we start our life close enough to the boundary that we see a piece of the tadpole, so the linear term, but we don't really break so much the effective theory, okay? And so, okay, so you can already also guess what I want to do with this, because if the scalar was actually starting his life somewhere here and then rolling down, and for some reason was arriving in the zone, in the area with the wiggles with small kinetic energy, or zero kinetic energy, or anyway, negligible compared to the value of the potential, then the moment you see a wiggle, you stop. And so dynamically, you're stopping where the Higgs mass is much smaller than its natural value, big M. Of course, to be able to do it, you have to get there with small kinetic energy. So one way to rephrase the hierarchy problem in this framework is that if you start at M, which is M Planck, you're right here with a kinetic energy, so let's say with phi dot squared, that is of order M Planck to the fourth. So if you encounter a wiggle that is of order lambda QCD to the fourth, you don't even see it. You like fly past it, and you get to minus M Planck squared for the Higgs mass before having any problem. And so the way in which you solve the hierarchy problem in this context is by somehow diluting this kinetic energy. And the way to do it is, let me imagine that there is some other scalar sitting around that is responsible for some inflationary phase. So its potential is flat, and it's somewhere much above the potential of my phi that is relaxing the Higgs mass. And so while phi starts its life somewhere at large field excursions, there is inflation. So the Hubble parameter is dominated by a nearly constant term, which is given by the potential value of this other scalar. If this is the case, well, we can write the equations of motion for phi in this background, in this de Sitter background, which is going to be the usual expression. So for the non-experts, what I'm doing is what I did also a couple of times in the previous lectures. So I'm coupling this relaxation field to gravity. Plus, okay, minus its potential. And then I'm imagining that the universe is dominated by this constant energy density. So I have the metric, so the line element is the usual homogeneous and isotropic one. And if I solve for Einstein's equations when the energy density of the universe is dominated by a constant term, as we've seen a couple of lectures back, I'm going to have a scale factor that increases exponentially. So then I plug back this metric into the action. I do the usual variation of the action to get the equations of motion, and that's what comes out. And to make this idea work, I need to imagine that this term here is much smaller than the other two. And this is just a choice, so I can do it by choosing the value of this Hubble parameter. And if this is true, I can this relaxation field is in a regime that people call slow roll. So its equation of motion is approximately this one. I can further assume, again, by choosing the value of this Hubble parameter, that the kinetic energy of phi, which now it's approximately this, is much smaller than the value of the phi potential, let's say, up to when I want to stop. Okay, so at least for phi up to the first wiggles. And again, this is essentially a choice of how much I suppress this motion from the friction coming from inflation. So I'm just choosing some other parameter of the model. So now it looks like we are essentially done. Okay, we just need inflation, which we likely need also to explain the CMB and other observations. You have written down a relatively simple model, modulo the caveats that I mentioned of the validity of the effective theory and the fact that phi is both a phase and not a phase. But so far it looks pretty nice. However, let's be a little bit more precise and see what kind of numbers you need to actually make it work. So first of all, you can ask, first of all, you need this Hubble to be small. So you need it to be smaller than lambda QCD in our universe. The reason is that if you are in this inflationary phase, so in this nearly de Sitter space, an observer inside the space, it has a two-point function that roughly goes like Hubble squared. This means that by quantum fluctuations in an Hubble time are moving phi by about Hubble. And you want the classical motion of phi to beat this. So we've seen that this is roughly of this order in an Hubble time. Okay, so this is through one Hubble time. And so you also need B prime to be much bigger than Hubble cube, okay? Because these quantum fluctuations are random. So if really they dominate, you might not even roll down. You might go up, then a bit down. Then in the end, so this was the requirement, again, on the initial model to simplify intuition and just make sure that phi was rolling down happily. But then later, some other authors have shown that it's not so crucial. So I left this requirement for last because it's not really so important, and it also doesn't put so much strain on the model as the other requirements. Okay, with this, we can stop and resume when the connection is back.
It's back.
It's back? Okay. Do you have a way to check where it stops so I can summarize very quickly what they missed online?
Well, after the slow roll, when you start the tableau, the
So
second
this
tableau,
whole second board was not okay. So well, I'm sorry for who was online because yeah, we kind of covered quite a bit of territory. So I'm also sorry for who's here because I'll repeat it, but quickly. So okay, let's say that phi is no rolling. Then you need a few more things for the idea to work as advertised. First of all, you need this Hubble that's driving inflation to be smaller than the QCD scale. So here I've forgotten a 1 alpha. The reason is that an observer in the Sitter space sees an effective temperature of order Hubble. And if the temperature is bigger than the temperature of the QCD phase transition, so roughly of the QCD scale, the potential with the wiggles does not turn on, as we said last time. A second condition is that phi has to move at least m squared over g. Otherwise, you might never even see the wiggles. And this can be translated into a number of e-folds of inflation, which is Hubble squared over g squared. And finally, you want phi to stop in the right place, so where the x-value is the one we measure. And if we just build this whole idea so that phi gets there with negligible kinetic energy. And so phi will stop when the derivative of its potential alone is comparable to the derivative of the potential induced by QCD. And this is this relation here. So M is the scale up to which you solve the hierarchy problem. So let's say 10 TV is the bare minimum. Otherwise, you've done all this work for nothing. F is a quantity that is bounded by astrophysics and laboratory experiment, because you can see phi through its axion coupling to gluons. And these are and this is the most generous bound I can come up with. If you plug these two numbers back into this equation, you will find that the G you need is 10 to the minus 21 GeV, the field excursion you need is 10 to the 10 M Planck, and the number of e-folds is 10 to the 36. There are ways to complicate this model and make this awful number much better. However, I know of no way of making this F smaller than the field, bigger than the field excursion. This is a problem when you try to complete the model, because essentially you're asking that the scalar be both compact, so be both a phase, something that is periodic with period 2 pi f, but also non-compact, so it's also a linear term that doesn't have any periodicity, and that's extremely hard to UV complete. Plus, your inflationary sector is quite special. It has a huge number of e-folds and a very small Hubble. So when you add it to the model, this adds extra complication. And if you really want to complete the story, you also need to add a sector that does meeting and doesn't spoil the fact that these wiggles keep phi fixed. So you essentially have to find a way to never give phi enough temperature that the wiggles disappear, or enough temperature that it can fluctuate past the point where it stopped. Okay, so this is a lightning summary of what you had missed when you were offline. Before stopping for the actual break, let me review the second of these ideas that I promised. So, and naturalness. And you will see that is very different. And so far, okay, you might feel like we have gone through a random collection of ideas, but after naturalness and after the break, I will summarize for you how all these different ideas that I presented in the context of a multiversal landscape kind of fit in a more orderly picture that you can even use to make contact with experiment to some extent. So, and naturalness. So the idea behind the naturalness is, let's imagine that you have many copies of the standard model. And they don't have to be exact copies, but for simplicity, let me imagine that they are. And the only thing that is changing between the copies is the X mass. The point where the X mass is 0 is not special, so you're going to have both sectors where the X mass is positive and sectors where the X mass, the X mass squared is positive, or sectors where the X mass squared is negative. we didn't really build a complete model of how this could come about. A sketch of why this could be the case is, for example, imagine that you have a strange brain that bends on itself, and then you have inflation, so that the bends exit the horizon, and then you are left with something that look like many copies of the standard model. Let's further imagine that there is a scalar in this extra dimension that has some profile, and that the scalar couples to h squared. Here you go, you have many copies of the standard model with an X mass that changes from copy to copy. Okay, this is just a sketch, not a real actual model. For a real actual model, you have to write the dynamics that gives you these bands, and the dynamics that keeps these let's say straight sections at a given distance from each other without collapsing. I mean, it's not trivial. But for now, let me just imagine that such a configuration with many sectors with different X masses is possible, and see what happens. So if this is possible, you might ask, well, how do I want to distribute? So what's the distribution of X masses throughout the sectors? And I'm going to assume that it's uniform, meaning that the smallest X mass is roughly whatever is the largest scale in this theory. Again, I'm imagining that at this scale m, there is some symmetry that protects the X mass. And so the smallest X mass here, if the distribution is uniform in m squared, is just m squared over the number of sectors. So this n is the number of sectors. I could have imagined other kinds of distributions, but most of them kind of imply that I already know the solution to the problem. So if I had made it more peak towards zero, I would have had to explain dynamically why. This is in some sense the most agnostic choice that I can make. If I do make this choice, you can already see that there are some numbers that are not going to make you feel comfortable, because let's say I want to solve the problem up to 10 TeV, then I need 10 to the 4 sectors. Let's say I want to solve it completely, then I need 10 to the 16 sectors, and I need 10 to the 16 and not 10 to the 34 because of what we were saying last time. If you have many particles, the fundamental scale of gravity comes down, and so when you have 10 to the 16 standard models, the fundamental scale of gravity goes to 10 to the 10 GeV, and this cutoff goes up to 10 to the 10 GeV, so you're solving the full hierarchy problem. Okay, this is just mentioning this for fun. So you might think that I've kind of already solved the problem, because I've imagined that there are all these sectors, and there can be some X masses that are accidentally small because of cancellations. However, I have to explain why we don't see any of them cosmologically. So let's say that we are the sector with the smallest negative X mass squared. Okay. This idea solves the problem only if we treat all the sectors equally. Okay. If we give, say, our sector a special coupling to the inflaton, we're not solving the problem, because the problem now is rephrased into the coincidence as of why this sector that has a small X mass is also the only one coupled to the inflaton. So this, let's say, brute force having many copies of the standard model is an honest explanation only if you treat all the copies equally. And so if you treat all the copies equally, you would expect that delta N effective, which is the energy density in the universe minus the one in the standard model divided by the one in one standard model neutrino, which is a quantity that we measure pretty well and should be, say, about smaller than 0.5 in several moments in the history of the universe. So at Big Bang nucleosynthesis, when the temperature was around MeV, and also at the CMB, when the temperature was around EV. We know that this number should be smallish than 1, okay? So the bounce is a bit stronger during the CMB, but this is a good ballpark. Instead, in this model, if we give all the sectors equal couplings, we're predicting it to be N. or actually n times 100 roughly, because 100 is the number of particles in the standard model. At least initially, n times 100. At these times, really something more like n. Order n times an order 1 number. And if you want to solve the problem at all, you need n to be 10 to the 4. So here you can see that we have a problem. But the nice feature of this idea is that the same relevant and marginal couplings that do generate a hierarchy problem to begin with are those that can be used to solve this an effective problem. So let me imagine that there is some sector doing inflation, would be our usual scalar friend. And then this sector decays to another sector, which then reads all these copies of the standard model. Okay, so there is an intermediate step between inflation and reheating, when all the energy density of the universe is in this reheating sector. There are different options for this reheating sector. The simplest one is if it's a single scalar. And let me imagine that this scalar is lighter than all the Higgs in our copies of the standard model. Then I can just write down, say, democratic couplings of the scalar to all the different sectors. This will be the most relevant, then there will be other couplings. And then I can ask, okay, how does phi decay? So how is delta and effective populated in this model? Well, I've imagined that phi is lighter than every X. So I can just integrate out the X's and get an effective Lagrangian for phi and the other standard model particles. And I'm going to have two different situations. One, when the X mass squared is negative, then the leading term in this effective Lagrangian is just this. Where psi are standard model fermions with some order 1 number in front, okay, coming from integrating out the X's. If, I'm sorry, there is a X web as well. So this is coming just from the diagram where you have a phi that mixes with a X through its web, and then the X is decaying to fermions. However, in the sectors where mh squared is positive, the leading interaction is instead this one. There are many others, of course, and we painfully computed all the decays of phi. So this is just, let's say, a condensed version, a very condensed version of the argument. But the leading decays of phi in the sector where the X mass is positive come from two gauge bosons. So they come from, so in this case, the two X's do not have a web. So you can get, so to integrate out the X's, essentially you always end up with some loop diagrams. For example, this one. You're going to have also decays to fermions. And you can include all of them in the effective Lagrangian for phi. But you can believe me when I tell you that these give you the leading decays. And so you can immediately see what might make the model work, because the couplings of phi to the different sectors are suppressed by inverse powers of the X mass. And, sorry, this is the I. And they are more suppressed for the sectors with positive mass squared than the ones for the negative mass squared. So even just staring at this Lagrangian, you know that you will put most of the energy into the sector with the smallest negative X mass squared. If you want me to be slightly more explicit, let's parameterize the X masses in terms of the smallest one. Times some index I. Okay. This is purely conventional. Then the energy density in sector I is the total one times the branching ratio of phi to this sector. So it's just the total one times gamma of phi to this sector over the total width of phi. Okay, let me call it this. And so you see from let's start with the sectors with negative x mass squared. And well, just a tiny caveat, which is not very important. It's just a factor of square root of 2, but it's important if ever in your life you want to reproduce the results in this paper. So it's not an accident that here I'm calling MH with a big H the mass, and here I'm calling MH with a small h the mass, and here with a big H, because so I'm calling MH capital squared the Lagrangian parameter. And this is the same as the physical mass in the sectors with positive x mass squared, but it's different by a factor of square root of 2 than the actual mass in the sectors with negative x mass squared. And so I'm always calling M, so this is the Lagrangian parameter, and this is the physical mass. Okay. And they happen to coincide only for sectors with positive x mass squared. But anyway, so this was just a small aside, which feels a bit out of place given how many squiggles I write in the lectures, but well, it's useful to keep in mind if ever you want to do these calculations. All right, so let's see what's the fraction of energy in these sectors. Well, I mean, you just essentially take the ratio between the width that you get from this coupling in different sectors. And so the width in sector I is going to scale. So here you have a VEV divided by a mass. This is going to give you the amplitude. So this is going to scale like MHI squared. So you square the amplitude. And so the ratio between the width in sector I and the total width is going to scale like 1 over I. So it's just the ratio of these two objects in practice. And so if you sum the energy densities in all these sectors, you have something that goes roughly like log n. So much better than before, but still way off the mark, because this is still log of 10 to the 4 at best. However, another nice feature of this idea is that the standard model is working for you. So this is true only up to the sector where the dominant x decay is still allowed. Okay, so let me say that I start from close to 0, and then I ask how phi can decay in all these sectors. Well, in the first few sectors, phi will decay to b bar, because this is the biggest Yukawa coupling of the x. But then at some point, as I increase the x mass and also the x vacuum expectation value, after some I, the B mass is going to be bigger than M phi over 2. And then this decay shuts off. And so phi from here on decays to charm, which is a much smaller Yukawa coupling. Well, much smaller, a factor of 5, but since it enters squared, it's good enough for us. And so in reality, when you do this sum, gamma I over gamma, well, what you're going to get is some log of 2, let me call NB the sector up to which you can decay to BB bar. But then you're going to have a suppression, y charge squared over yb squared times log of 2 and charm. And then there's another threshold. So then at some point, also the charm quark will become too heavy, and so on. And so the sum is actually not UV sensitive. It's not dominated by the heaviest sector. It's dominated by the lightest few sectors. And well, if you look at the numbers, this is still quite not enough to make it work, but it's close enough. So I refer you to the papers for more details on how to make it work. The basic parametric idea is this one. So what happens if you look at the energy density as a function of sector in the sectors with negative x mass, it does something like this. It goes like 1 over I, but then it drops, and then it goes like 1 over I, drops, and so on. Now, okay, we're almost done. Huh? You can just wonder what happens to the other sectors. But here, well, the other sectors are actually much more friendly, because as we've seen already from the effective Lagrangian, the decay width goes like 1 over mx to the fourth. So it will scale once you divide it by the total width. It will scale like 1 over I squared. So you see that these sectors are much less important. Already, without even considering any extra detail, you already see that this is purely IR dominated. So the sectors with large n don't matter at all. So essentially, you have only to worry about the nearest one. And again, this is not quite a proof that the model works, but we did all the calculations in painstaking detail for 10 to the 16 sectors, and it does work in some limits of the parameter space. So I refer you to the paper for more details. But the basic point is that we've seen something very different from before. So we still have a landscape. So we still have many realizations of the Higgs mass. They're all in our universe. They're all in causal contact with us. In principle, so there's going to be, for sure, gravitational couplings between us and this other sector, which is why you can see them through delta and effective. And I wanted to tell you about this idea because it's really very different from everything that we've seen before, especially in its predictions, because its zeroth order prediction is delta and effective. So you're going to see something at CMB stage 4. And if someone had told me 10 years ago that the first hint of why the Higgs mass is small would be delta and effective, I would have laughed at them. But this could be the case. And then the second, let's say, smoking gun signal of this idea, which, however, is very futuristic compared to the capabilities of current cosmological experiments, is that since you have a little bit of energy density in all these sectors, and the neutrino in all these sectors have slightly different mass compared to ours, they leave an imprint on the matter power spectrum at a slightly different scale. So if you had infinite resolution and you measured the matter power spectrum, so essentially the distribution of dark matter, as a function of wave number or size, how big a cluster is, if you could zoom in really precisely, you would see all these tiny little steps, which correspond to the neutrinos of the different sectors starting to free stream. Okay, this would be like an insane smoking gun signal of this model, but if you look at how much resolution you need, it's probably not within our professional lifetimes, but who knows? Experimentalists always tend to do better than what they promise you, so I'm optimistic. Anyway, so this is, I think, a good place to stop, both time-wise and logic-wise, because now we kind of, I've exposed you to a big range of ideas on how to explain the Higgs mass in the multiverse, but it's a good time to kind of wrap up. So to see if all these ideas that look so different from each other have something in common, have a common structure, maybe can be detected or cannot be detected, and that's what we're going to do at the beginning of the next hour. After which, I'll give you a broader summary, including in this recap also the symmetry-based solutions that we've seen at the beginning. And then if time permits, which I think so, we will go to the crazier stuff, like UV-IR mixing, non-invertible symmetries. Ideas that don't work, but I'm more optimistic that you haven't already heard about. Okay, so let's take our break.
So maybe there are questions.
Sure, yeah.
So, question, you mentioned the fact that you would have in the different sectors different masses, right? So I don't understand why you don't expect to see this effect more easily, because the next generation of surveys will measure, will go very close at least to measure neutrino masses. So,
Well, so yes, but so these other sectors have a small fraction of the energy density. Um, so this is like, okay, so I don't have a quantitative way to prove it to you. So some groups have done a careful analysis, like in Dalal, I think. I mean, they really like went there, simulated the naturalness in the power spectrum, and found that it was not observable. But the short answer is just that if you want to be consistent with delta and effective, the energy density in the neutrinos of these other sectors is too small to see that. Yeah. And if you ask me to really run the numbers for you, I cannot do it live.
it's fine. The parameter was missing.
Yeah, but actually an interesting point along these lines, instead what you would see is that this delta and effective is made up of two components, a free streaming part of radiation and a non-free streaming part. Because in these sectors with MH squared positive, all the fermions are very light. So essentially electrons and photons never decouple. So that's acute, let's say, smoking gun prime signature of naturalness. That not only you see delta and effective, but you see also that a piece of the radiation is not free streaming. So we've seen a collection of ideas to explain the Higgs mass and the cosmological constant in the multiverse, and they might all look different from each other. It's because they are, but they also have something in common. So we always have, okay, this description is so schematic that it's kind of obvious that it applies, but let me do it anyway, because it might be helpful to organize our ideas. So we have a symmetric sector, and then we have a coupling, symbolized by this dashed line, and then we have a standard model landscape. So for the last ideas that we've seen, for example, for the relaxion, the symmetric sector is phi itself. When G goes to 0, there is this shift symmetry. And so it's natural to take G much smaller than the largest scales in the theory. And this is what is fixed in the weak scale. So the weak scale can be small because this G can be small. Then the coupling was this GG tilde operator. And the standard model landscape was built in the model to this coupling. So as you were rolling down the phi potential, you were seeing many different values of the Higgs mass. For naturalness, the symmetric sector was again our reheating sector, whose mass was smaller than the smallest mass. And we didn't say it explicitly, but this was technically natural because we have nothing stops us from making the coupling of the scalars to us small. The connection here, so when I say a coupling, I really don't want to just write down the interaction between the standard model and the symmetric sector, but what I care about is the interaction that is selecting the Higgs mass. And as such, it has to be sensitive to the Higgs mass. And the object that was sensitive to the Higgs mass in this story and was allowing us to put most of the energy density to the smallest sector, and so single it out as our own, was a non-local object. Okay, so here we had an operator depending on a single space-time point. Here we have a two-point function. So essentially, what I mean by a two-point function are the masses of the standard model particles. So the d quark mass, the charge quark mass. These are all objects that you can extract from a non-local quantity, so a two-point function. And the landscape was this collection of sectors, potentially all in causal contact with us. For the statistical selection idea that we've seen, let me call it attractor vacua. The symmetric sector was the one of the four form, for which we could write naturally a charge that was smaller than its natural value. So this is a charge per unit area. The coupling was through the charge itself. So it was this object sensitive to the Higgs-Web, which we've written as this local operator to the n. And the landscape was given by the coupling of the fourth form to the Higgs. This was just today, but we can map into this table also what we discussed on previous days. And maybe, well, the most interesting for you will be how to map anthropics into this table, because usually you don't think about anthropics as coming from a symmetry. You can see here that in all these ideas, in the end, what was really stabilizing the Weak scale secretly was a symmetry. Okay, it's a bit unfair to say in this case, to say the word stabilize in the case of a naturalness, for example, or in the case of statistical selection, because the Weak scale is not really stable in these models. It's just accidentally small. But what's selecting the value that we observed was a symmetry. And for anthropics, so anthropic arguments, it's the same. So if you remember, the core of the idea that we discussed last time was that if you make the Higgs-Web too large, the neutron-proton mass difference becomes too large, and all nuclei decay, only hydrogen survives, there is no complex chemistry. And so essentially here, let me start with this part, okay, which is more obvious. What's the coupling that is selecting the Weak scale is, again, this non-local object that's given by the masses of the quarks, mostly. The standard model landscape is just a multiverse, okay? Let me write it, let me draw it as this collection of bubbles. And the symmetric sector is QCD, okay? The only reason why anthropic arguments work at all, it's because the QCD scale is not so far from the observed value of the Weak scale. And what's protecting the QCD scale, as we've seen in the first lectures, is scale invariance. So again, if you want to be a bit provocative, you can say that anthropic arguments only work because of scale invariance. So composite Higgs and anthropic arguments are not so different. I shouldn't have said this on record. It was just a joke. But what else? So So another idea that we've seen was this crunching idea. And there, the symmetric sector were these two scalars, phi plus and minus. And what was protected by the symmetry was their mass, m phi plus minus, which again could be naturally small because of a shift symmetry. Then, so you needed actually two ingredients. You needed this mass to be small, which is actually what's selecting a small value for the Weak scale. But in this case, you need also a second symmetry that explains why there is this big hierarchy between the two minima of phi plus and minus. We didn't really talk about this in detail, but if you really want to write a UV complete model, which we didn't have time to do last time, you need to add supersymmetry or scale invariance to explain naturally this big hierarchy, because you want to crunch all the time when you are in the deep minimum, but you want to be fine when you are in the shallow minimum. And so it's not, modulo having a symmetry, you wouldn't have a potential looking like this. The connection was, again, this GG dual operator. and the landscape was a multiverse. And okay, I think that this summarizes the main ideas that we've seen for the X-mass in the context of multiverse. And there are many more, however, but they all fall into this schematic form. And again, you can tell me it's so schematic that of course they do, fine, but I think it's still a useful mnemonic device. The second useful mnemonic device that I propose is this differentiation between statistical, anthropic, and dynamical selection that I've explained at the beginning. But the reason why I've drawn this table is mostly because you see here that there is one ingredient that appears more than once, and it appears even more often if you consider other ideas. And it's also the best shot we have at detecting these ideas, which is that here in the middle, we have, okay, in some cases we have these 2-point functions that exist in the standard model, whatever. But in many other cases, we have these local operators that depend on the X-band. And these are quite unique objects. So it's not at all trivial to find a local operator that depends a lot on the X-band. What do I mean precisely by a local operator depending on the X-band? So let me delete this part of the table. So we all agree, I mean, just based on pure logic, that if you want to select the X-mask, you need some ingredient in your model that depends on the X-mask squared. More importantly, you need something that depends on it strongly. So if you take some observable, whatever you want to call it, and ask what's its relative variation when you change the X-web, it has to be order 1. Okay? This is kind of obvious because imagine that, I don't know, let's take the relaxon just for concreteness. Let's say that these wiggles change very little when you change the X-web by a lot. Then stopping here or stopping here would make no difference. So you would not be singling out the wig scale with respect to M plug. They could be the same. So you really need something that changes at order 1 when you change the X-web at order 1. And my claim, well, I have 2 claims. The first one is that in the standard model, the only local object with this property is GG dual. And so this is already an interesting fact. So by thinking about this multiverse, we learned an important fact about the standard model, which there is only one local operator that depends at order 1 on the X-web. And interestingly, it's the same operator that is related to another problem in the standard model. So why the neutron electric dipole moment is so small. Let me show you that this claim is true. Then my second claim will be that not only this is the only one in the standard model, but even if you allow yourself infinite model building freedom, I know of only 2 more. Literally infinite model building freedom. But let me start by proving my first claim, okay? My first claim is that the web of this operator is the only one that has this property. Okay? So if I now ask if my observable is the vacuum expectation value of a local operator in the standard model, the only one for which this order 1 number is true is this one. And okay, not very precisely, but we've already seen that this is true for GG dual. So we've seen that it does change at order 1 when you change the X-web at order 1. But let me be a bit more precise. So how do you compute the web of a local operator? Well, it's simple. Let's say you start with a Lagrangian that contains the standard model plus some probe scalar with a weak coupling to the operator that you want to compute the web for. Then you integrate out the standard model, and you're left with an effective Lagrangian only for phi. Okay. That will contain a potential that is a function of the coupling times phi. If you send the coupling to 0, it goes to 0. And in particular, you can expand it for small coupling. And you're going to get that the linear term is the web of the operator. So let me give you a simple example. Let me say that this operator is h squared. Here we are integrating out the standard model. What happens when let's say I couple phi like this to h squared and I integrate out the standard model? At tree level, I just have the x web squared. If you want, the diagram is just this. At one loop, well, now I have this, which is gonna give me whatever. So let me put a hard momentum cutoff on to regulate the loop. Then I'm gonna get this. And then, well, I can keep going, but this is already enough to illustrate my point. So if I do this procedure, then I would conclude that the web of h squared is v squared plus this large scale, 16 pi squared. Okay. And so when I take my log derivatives, I'm gonna get that so just to be more explicit, this just means v over h squared times the h squared web over dv. And this is just if m is much bigger than v. So if I add no new symmetry up to some large scale, then I'm getting essentially the hierarchy problem. So I'm getting that this maximum expectation value changes very little when I change the x web at order 1. And so this is, you see immediately that this is not a good candidate for these ideas. Because if I had coupled the relaxation or the crunching scalars to this operator, either I would have solved the problem by asymmetry already and put this m, well, here I even neglecting the factor of 4 pi. Okay? The factor of 4 pi helps you a little bit. It doesn't really matter. So either I already solved the problem with another symmetry that brings m down to v times 4 pi, or this operator is doing nothing for me because it's changing so little when I change v at order 1 that it's not selecting the x mass that we observed. This was one example. So you might think that you might still think that I'm lying to you, but let me give you another example. So let's say I couple it to a Yukawa. This example with the Yukawa is perhaps more illuminating. So again, at tree level, I just have the expectation. Let me imagine, so this phi is really much lighter than all standard model scales. So I'm computing this below the QCD scale. And here I'm going to get the web of the quarks after QCD confines times the web of the x at tree level. At one loop, again, I'm going to do the same as before. Sorry, at one loop there is nothing, but at two loops there is this. And I can always close the loops because the operator is in the standard model. So in the standard, so we started with this Lagrangian that contains the standard model, and lambda standard model contains the operator itself. So I can always put an insertion here and close the loop. And this is true for all standard model operators. And again, this loop is UV sensitive. And if I put some cutoff, actually here there is even not necessarily a Y. So I'm coupling, say I'm coupling F to the operator in this way, okay? So now I just have, again, my arm momentum cutoff to the fourth. And so again, if I do this exercise, I'm gonna find that the change in the value of this operator is of order this divided by m to the fourth. So again, I have a tiny change when I change the x value by order 1. And I could do this for another 2 hours for the standard value operators, and we always would get the same result, for the reason I just said. And if you want, this is yet another manifestation of the hierarchy problem. If you want, you can call this the hierarchy problem. The only one for which this is not the case is this GG dual. And the reason is very simple. The reason is that you can rewrite this operator as a derivative. So if I couple a scalar to this operator, I can always integrate by parts and find that at the perturbative level, this is doing nothing, at least to the potential of phi. So if I try to repeat my exercise of integrating out phi, and I put loops of gluons for the tupole, the quadratic term, the quartic term, whatever you want, you will always generate terms with derivatives, never a potential. The VEV of GG dual comes from non-perturbative QCD dynamics, and it's saturated at the QCD scale. So that's why I've always traded this coupling. Well, let me forget about that, but I always traded this coupling for those potentials that were of order this times some function of phi over f. So the reason why this is saturated at the QCD scale is that one can show that, well, we already with this simple exercise, you see that perturbatively, this operator does nothing. So it doesn't have a vacuum expectation value, and it doesn't affect the phi potential. Non-perturbatively, well, okay, really doing this properly would require another hour, as I was telling Patrick, asking a question offline. But let me just tell you why it's the case that, the value of this operator and the potential generator for phi was saturated at the QCD scale. The reason is that the leading non-perturbative effect that makes that gives, I mean, that generates these things that we are interested in is a classical solution of the equation of motion called the instantons. This classical solution, the vector potential goes like 1 over r cubed, if I remember correctly, when r goes to infinity. Even if I got the power wrong, the conceptual point here is that it goes to infinity, it goes to 0 at infinity, but not very fast. Because if you look at the action also goes as an r cube in the integration measure. And so when you put GG dual and you evaluate it on the classical solution of the equation of motion, you get something that is non-zero. You get some constant. Okay. This is a semi-classical approximation to the path integral. Essentially, you're doing a saddle point approximation, and you're saying that, okay, I'm doing it in Euclidean signature. The path integral is approximated by the action evaluated on the classical solution to the equation of motion. And at small coupling, so let me, but at small coupling, one can show that this is the leading non-perturbative effect. The reason why this is a good approximation only at small coupling can be understood just by looking at the kinetic term. So you can always write the kinetic term in this way. So in the path integral, you have something, if we restore units to h slash, that looks like this, okay? And so a saddle point approximation is a good approximation only when this is very small. So only when you're at small coupling. Okay, this is all very heuristic, but these statements can be proven. And this in particular shows you that at high energies, the effects that matter for this operator go like e to the minus 1 over coupling squared. And the QCD coupling at high energies, at least in the standard model, goes to 0. So high energy corrections in principle can enter this operator, but are very suppressed by this semi-classical factor. I realized that this was very quick and unsatisfactory. Unfortunately, to prove all the statements that I just asked you to trust me on would take a fifth of the course, or maybe more, maybe half of the course. So unfortunately, this is the best I can do in the time allotted to these lectures. But now let's close this digression and go back to what was our main point. So our main point was that you need these objects sensitive to the X-web to construct these solutions. And if you ask what are the local objects that are sensitive to the X-web, you have a limited number of available choices. In the standard model, there is only this guy. We didn't really prove, I mean, wrote a formal proof, but I hope that my arguments convinced you. If you allow yourself, as I was saying, infinite model building freedom, I know of only two other options. One is to play the same trick. So let's add a new confining gauge group, similar to QCD. Let me call the field strength of the group F. This operator can play the same role as GG dual if you add also some new fermions that couple to the X and are charged under this confining gauge group. Let me say that the potential contains this. So the reason why I need to add these new fermions is that the web of this operator was depending on the X-web through the pion mass mostly and the QCD scale. Okay, so it was roughly of this order. If you unpack what this means, well, the pion mass depends linearly on the mass of the quarks and on the scale. Sorry, the pion mass squared. And the mass of the quarks is the object that depends on the X-web. F pi also depends on the X-web with some power of roughly 1/3. And this is due to the fact that F pi is the scale when the QCD coupling runs strong. So if you, let's say, draw the running of the QCD coupling versus the energy scale, and it will do like this. But more precisely, whenever you encounter a threshold, say the top, the beta function will change a little bit because below you're integrating it out, so the top is not contributing to the beta function anymore. And same when you encounter another threshold, like the bottom quark. So at every threshold, at every mass, the beta function changes a little bit. And so the masses of the quark also determine where this F pi, so where the scale where QCD becomes strong is. And that's why the scale depends on the X-web, because the masses of the quark move around if you move around the X-web. And so the only way to replicate the sensitivity of this operator to the X-web in this theory where you added a new gauge group is if you also add fermions that are charged under the gauge group and have a mass that depends on the X-web. Okay, and this discussion also shows you that the mass of these fermions cannot be, so even if you add this vector-like component here that doesn't depend on the X-web, this vector-like component cannot be too far from the X scale. Because, again, we are relying on something that changes at order 1 when you change the X-web by order 1. If these mass scales were much, much bigger than what comes from the X-web, then you would be again in the same problematic situation that you are in the standard model for other operators. And this is actually why it's so hard to build an operator that is sensitive to the X-web at order 1, okay? Because you cannot add mass scales that are bigger than the weak scale, not 4 pi the weak scale, really the weak scale. And so it's really an experimental problem. You can find as many operators as you like that are sensitive to the X-web at order 1, but most of them are experimentally excluded. This one is not. The other one that is not, but it almost is what I was using before, this H1, H2. So you add a second X doublet, and then you build your Lagrangian such that it's invariant under this symmetry. Then this symmetry essentially is such that the selection rules tell you that here you cannot put, let's say, the biggest scale in your theory, because this biggest scale in your theory in general will be even under the symmetry. You can only put something that it's also odd. And typically the only thing that you have in your theory that it's odd, if the theory is invariant under this symmetry, are the webs of the two. And it's maybe implicit in this discussion, but you see that you cannot make the mass of the new X doublet much bigger than the weak scale. Otherwise, again, here you would have something that looks like, say, V1 times big M. And when you take your derivatives, this object doesn't depend at order 1 on the X-web anymore. Okay. So these are the only 3 objects, and they kind of give you some hope of seeing these at colliders, at least in these 2 cases. So you're predicting new vector-like fermions charged under SU2, or a new X doublet charged under SU2 with masses close to the X mass. To be completely fair, I'm being quite demanding when I say that there are only these 3 operators, because if you're willingly to have some cutoff, say you have some symmetry above some scale, then there are also other operators that might do the trick. Okay, so you can recover this order 1 here in some cases where this M is small enough. Okay, for the dumbest operators like H squared, you really need this M to already solve the hierarchy problem for you. But you can build more clever operators whose webs are protected not by exact symmetries of the standard model, but by approximate symmetries of the standard model, like flavor, for which, when you compute the web, you get a bunch of small couplings in front of the big scale. And you can live with a scale maybe that is not M-Planck, so this tree can allow you to solve the problem even if the scale is M-Planck, but it's also not 1 TeV. Okay. One example would be, for example, just to make this idea more concrete, this guy. Let's see, so this is, yes. So for this operator, again, if we do the exercise that we did before, so if you want to close all these legs, you need to put small insertions of the Yukawas. Let's say that these are really the up fork and the down forks. Then these couplings here are of order 10 to the minus 5. So even if you get from dimensional analysis a big factor of m to some power here, when you redo this trick, you're going to get a b squared over y up times y down times this m squared. So this might allow you to go to, say, I think of order 100 TeV, 50 TeV, maybe with this scale, before you have to use another operator, and this doesn't do the trick anymore. And so you can ask yourself what's the full list, but the bottom line, so I don't want to digress too much, the bottom line is that there is a limited number of these objects. Only 3 can solve the full hierarchy problem. Only some other countable set can solve it up to some scale. And so you see that even if we started despairing that we could never see any of it at all in our lives, instead, a big subset of these ideas that explain the Higgs mass from landscape or multiverse considerations have very testable consequences. And okay, this is the only time, I will express a personal opinion, or maybe I've done it already a million times without noticing. But I also feel that these ideas that couple to local operators are kind of the most robust in some sense. Because if you remember, so with the exception of naturalness, now I deleted the list, but if you remember, the anthropic arguments that do not rely on these local operators are very detailed. So they require complex chemistry to be exactly the one in our universe, otherwise you have no observers. But it's not guaranteed at all that you cannot have observers in another way. These statistical selection mechanisms, instead, they're all plagued by this problem of eternal inflation. So they essentially can never prove their claim that the X-Web close to the one that we observe is the one that's most likely in the universe. So to me, the ones that really rely on a model that you can almost feel from the beginning to the end and really see at work are those that couple to local operators. Maybe with the only exception of naturalness that I've shown you precisely for this reason. Because on the one hand, it's an exception, but on the other, it has other testable consequences that are also very unique and interesting. So, how much time? Oh my goodness, I'm already essentially run out of time.
Well, let's say that you have, I don't know, how much time do you need?
Well, let me wrap up my summary, and then because I'm gonna, let's say, completely betray my promise of talking about the crazy stuff, because this up to here, this was the conservative stuff, but the truly crazy stuff was supposed to be this last hour, but I took it up entirely for the summary. Well, let me go very quickly to, let's say, the global summary.
Raffaele, maybe you have, say, half an hour.
Okay, then that's very good. So I'll go very quickly to the global summary.
Don't rush. I mean,
Yeah.
well, rush, but
Not too much.
Maybe if
Yes.
you don't have the time to discuss all the crazy stuff, maybe I personally would be more interested in generality.
Sure. I mean, I should prevent you that you'll be very disappointed.
Okay.
But in the sense that it's interesting that it's clever, but it doesn't work at all for the action. And also, it's kind of, the idea that it's relevant to the hierarchy problem is not the most emblematic of this generalizing. It's kind of a very simple application that actually tells you more about basic statistical physics than about this generalizing. So, but I try to say something before the end. Okay, so if you remember, in the first lectures, we kind of made a list of possible explanations for the Higgs mass and the cosmological constant. One, well, was just tuning. So maybe they're accidentally small. This is possible. You have to live with this conceptual possibility. But it seems very unlikely because we never encountered in nature anything that was so small because of an accidental cancellation. At least for the cosmological constant, never ever, except for the cosmological constant. For the Higgs mass, at the moment, if you really stick to experiment, so if you say that we have a cancellation at a few percent level, we have seen other instances of such a cancellation, but already if at the next collider we see nothing, that would be the most accidental accident, if you allow me, that we've seen in nature. The second option was symmetry. And this was a possibility for the Higgs mass, but not so much for the cosmological constant. Then lowering M Planck. And again, this was a possibility for the Higgs mass, but not so much for the cosmological constant. And in both these cases, well, okay, we have seen a few examples. So if you really want a complete summary here, we've seen mostly supersymmetry and scale invariance in the form of warped extra dimensions, and to a lesser extent also composite Higgs, which can be related by the DSCFT correspondence. And then in this case, we've seen just large N large extra dimensions. But large extra dimensions, depending on how you stabilize the volume, can also fall back into this category of symmetry. Not well, let's say that's this general category. And we've seen that in both of these cases, you predict new particles not too far from the X mass. I mean, in the best case, a loop factor above, okay? New particles or new dynamics, I mean, to see phenomena that we have not yet observed in the standard model. This was a common prediction. Maybe the case where we've seen it less convincingly is the case of warped extra dimensions. I was counting on doing it that today, but I don't think we have enough time, but I put it in the notes. So I mean, the only argument I ran in this case was that this case, by a rescaling of the metric and of the fields, is equivalent to this case, and in this case, the fundamental scale of gravity is a TV. So also in this case, you expect new physics on a TV, but we didn't really do the exercise of expanding the 5D theory in fluctuations of the metric, integrating out the extra dimension, and seeing that the fluctuations of the metric indeed are predicted at the weak scale. That's in the notes. I wanted to do it today, but without having enough time. Then, okay, in the last couple of lectures, we talked about the multiverse and landscapes. And we've seen that under this name actually fall many ideas that are quite different from each other. Today was a prime example of this. And the main reason why I take this seriously is twofold. The first one is that essentially the only concrete explanation we have for the cosmological constant comes from here. You might argue on the details of the construction, whether it's really compatible with string theory, or there are tensions in building the zither vacuum or not. But if you tell me, do you know of any case where you can build a model that explains the cosmological constant and not just wave your hand? This is the only option I know. Okay? Maybe you know of others, but I don't. And the second reason why I tend to take it seriously is that if you have a theory with more than 4 dimensions, like string theory, you typically have many vacua. If you pair this to inflation, it's likely that you might end up with a multiverse. It's not guaranteed, but it's entirely possible that this happens completely independently of these problems, that we're just forced to think about a multiverse. Of course, this doesn't mean that symmetry as ideas are excluded. I mean, you can very well have a multiverse with a symmetry, and actually, if that's the case, you will most likely see that MH squared is explained by a symmetry, because in all the ideas that we labeled multiverse or landscape, we were actually saying that MH squared was small because of an accidental cancellation, and so only a small number of universes in the multiverse and a small x plus squared. But if instead there is a symmetry, well, the distribution in energy of the symmetry breaking scale can be anything. I mean, it can naturally be small. So if you just ask very naively, knowing nothing about the UV structure of the multiverse, what you expect to be more likely, if the symmetry breaking scale is small or that the X mass is accidentally tuned, you would say that the symmetry breaking scale is small. And then, well, we had also listed a few more adventurous options. So some UV IR mixing that gravity maybe doesn't have a scale. And I forgot what was the last option that we said, because I mean, I'm listing these options for completeness, but they're not attached to actual ideas that work. Yes. Option number 6 was just, in some sense, the trivial one, that MH squared and the cosmological constant are never calculable.
Sorry, whether you put the relaxant in that picture?
Well, in this landscape category, I would say. Yeah, I mean, of course, all this is arbitrary. You can choose a different categorization, and there are people that would argue with you for days about this. In reality, I mean, the people that would argue with you for days, usually they do it because they have an agenda, because they want to like prove to the field that all options in these categories should just be ignored. Okay. Exactly. Yes, except their ones. But okay. But since here we are all in good faith and have no agenda, I think we can just be happy that we have some categorization to remind ourselves of what are the conceptual options, and then, okay, if you want to move an idea from 2 to 3, I don't care. Actually, even I don't know exactly where to put large extra dimensions. I mean, depending on how you stabilize the radius, you could call it something or something else. So, okay, you might feel that the way we distributed attention was very unbalanced. I mean, we devoted all our attention to 3 items on a list of 7 or 6, depending whether you want to count tuning. But okay, the reason is easy to explain. Let me give you an example of what I mean by UV-IR mixing. Okay, in this category, again, I'm uniting two things that are very different. One is consistency of quantum gravity. So maybe this set of researchers that are thinking about what effective field theories can embed it into string theory, one day will prove that only theories with 0 cosmological constant and 0 X mass can be embedded into string theory. This is one option. The other option is more, let's say, mechanical. Okay, so if you compute the X mass at the scale where you measure it, so let's say at the measured X mass itself, okay, let me call it an infrared scale. This is gonna be given by the X mass in the UV, so at high energies, plus some integral of contributions. Could it be that this integral behaves non-trivially and there is a connection between high and low energies that explains why these two pieces are canceling to give you the small one that you observe? In effective field theory, you would say, obviously not. I mean, you can just estimate this and this by dimensional analysis, and you know that this should be of order lambda UV squared. Okay, we've done this exercise in painful detail the first time. However, okay, I mean, you know that quantum gravity to some extent wants to mix high and low energies. Okay, the dumbest way to see it is that in quantum mechanics, you would say just from Heisenberg's principle that short distances are related to high energies and vice versa. So here there is an H slash if you want, and there is also a C, okay, if you really want me to put all the units. But quantum mechanics is telling you that short distances are high energies. However, GR would strongly disagree. It would tell you that large distances are also large energies, and vice versa. So just by this very, very dumb parametric argument, you might expect that when you try to do this calculation, including quantum gravity, something might go wrong. The problem is that no one, as far as I know, can go beyond this dumb statement. So there is not an actual model where you can do this calculation and see this effect happen, except for the one I'm going to tell you now. Okay, let me imagine that we live in a different world where Lorentz symmetry is broken at order 1 by the fact that space-time doesn't commute. Okay, my x coordinates are operators and they don't commute. This is creating something like what we are interested in, so some mixing between high and low energies, because the Heisenberg principle for these operators would read something like that. What happens in this theory when we try to compute the Higgs mass? So one can show, and I'm just going to tell you without proof, that you can do quantum field theory on these spaces like ordinary quantum field theory, provided that whenever you have two fields at the same space-time point, you multiply them according to this rule. Okay. Don't ask me to prove this because I don't know how to do it, but I believe it's true. So so the first thing that you will notice if you try to write, for example, the theory of a scalar field in 4 space-time dimensions that are non-commutative is that the kinetic term and the mass are the same. Let me do it in Euclidean signature because these theories are a mess in Lorentzian signatures. This is due to the fact that if you add the momentum conserving delta function to this product, this exponential goes to 1 when you have only 2 fields. You can see it relatively easily in momentum space. Say you have n fields that are multiplied. Then the corresponding term in the action will look like, okay, some product, these are n, of your Fourier transformed fields times a delta function of the sum of momenta times the Fourier transform of this. And here the sum is on all j is different from I. If you want j is smaller than I. If you here put only 2 fields, the momentum conserving delta function will set this to 1. Yes.
K are not operators, right? They're
The K are just moment. Yeah. Well. Yeah. So as I told you, you can treat even space-time coordinates as ordinary coordinates, not operators, provided that you replace all products with this. So yeah, the K's are numbers. So okay, so in this Lagrangian, my phi the 4th term does have this funny product, but the phi squared and the kinetic term don't. Okay. So now, okay, you can compute the correction to the mass coming from the one loop diagram with the quartic coupling, and you're going to have the usual diagram. Let me say that the external momentum of the scalar is p. But in this theory, you have also to distinguish this non-planar one from the usual one. So in the normal phi to the 4th theory, these 2 diagrams are the same. But in this theory with the exponential, these 2 give you different results. Indeed, if you write down the amplitude for this for the planar one, so this is the planar one and this is the non-planar one, you're gonna get this. So in the planar one, I can set to 0 the external momentum, no problem. In the non-planar one, I'm gonna get one small difference. So again, in the numerator, I'm gonna set to 0 the external momentum because it doesn't matter. But in the non-planar case, this exponential is non-trivial. And let me check again, not to make any mistake, what are the factors of 2? Let's see. not much time. Yeah, so you get yes, k mu theta mu p mu. Okay. So maybe I should go a bit faster than I was expecting, but in any case, so you can do the first integral with standard techniques. So let's say I regulate it with a hard momentum cutoff. If I regulate it with a hard momentum cutoff, I'm gonna get lambda squared minus m squared log of lambda squared m squared plus some order one numbers that we don't care about. To do this other integral, it's usual to Schwinger regularize it. Sorry, to use Schwinger parameters and write the denominator as this. If you do it, then let me continue. Yeah, so if you do it, you're gonna get the following, where I've already done the integral over k to save time. I'm gonna get this. Again, I have to regulate it with somehow, and then again, I'm gonna choose an hard momentum cutoff that I can, in Schwinger parameterization, I can write like this. If I do this and then do the integral over alpha, I'm gonna get formally the same result as above, but with a lambda effective that contains also this term, where lambda effective is where this p circle p is just defined as minus this object here. Okay, I'm almost done with this example. You will see in a second what I'm getting at. So now let's write the 1pi effective action, okay, and see what happened. First of all, I'm going to add a counter term and regularize the scalar mass. So the usual, as you can see in the planar, from the planar diagram, we still have the usual term that needs to be regulated. And here, up there, I forgot a factor of pi in the denominator. But now, well, it's it. Yeah, so the first thing that I need to do is to regulate the usual divergent integrals. So I'm just going to define big M as this. Plus also the order one numbers if you want. It doesn't really change much. Then I can write my effective action for the 2-point function as this. Let's see, is the new one. Yeah. plus the non-planar one, right? So in the non-planar one, I have this plus I have, sorry, minus m squared. Now it's a big M squared because I've regulated it, lambda effective squared over big M plus order 1 numbers. And here, okay, I have here I have a factor of g squared over 96 pi. And here I also have a factor of g squared over 96 pi. And I have the Fourier transform of my initial field. Okay, so this is the new 2-point function of my scalar. What's interesting is that I start, let's say now I send lambda to infinity. Okay? Lambda is an artificial regulator, so if I am a Wilsonian effective theorist, if I send it to infinity, everything should be fine. Indeed, okay, my counter term takes care of it, so I just imagine that m is the measured mass of the scalar. And what's interesting is that the non-planar diagram is totally finite. Okay, if you remember here, this lambda effective, I've written it explicitly here. So when lambda goes to infinity, lambda squared effective goes to this 1 over p circle p over 4. However, if I do this, there is a infrared pole that didn't exist before. So now, if this p circle p is equal to minus g squared over, I think, 24 pi m squared, I don't have the most updated notes in my hand, so I forgot what are the order 1 numbers, but I recommend you check them on the PDF notes. You'll find that, okay, there is this other pole. This is not yet a mass, okay, because if you remember, this p circle p was a p squared times a theta squared, and theta has dimensions of 1 over energy squared. So let me say that this matrix theta mu nu has only one eigenvalue, lambda theta. Then the pole really is at minus g squared lambda theta to the 4th over 24 pi m squared. So I'm not sure that this pi is really there, but it doesn't matter, okay, for the main message. The main message is that I started with a theory that is UV sensitive, but then I found that after I regulated in the usual way, okay, I do have a hierarchy problem for the scalar, so this big M has a hierarchy problem, but I've also generated a new pole, which in principle is stable under radiative correction. So this new pole knows nothing about high energies. It only knows about this lambda theta scale and the mass of the other scalar. Actually, even if I take the mass of the other scalar to the cutoff of the theory, and I make it big, as it naturally wants to be, this other pole in the propagator becomes smaller, so it goes down. And, well, if you look at it without thinking about it too much, it almost looks like magic. So I started with a UV sensitive theory, and then I generated from high energy dynamics a pole in the low energy theory. What's even more intriguing is that if you try to write an effective theory, so attach a particle to this pole, you will see that it's not possible to integrate out phi, which supposedly is the heavy one, and have a theory, a low energy theory of just this light pole. They're always mixed in a non-trivial way. I'm not going to do it for you because I'm already running way too late. But, okay, if you think about it instead for a moment longer, this is a bit less surprising than it appears. Because really this pole is related to the scale where the Lorentz symmetry is broken. So in some sense, it's not crazy that you have another stable scale because you've broken another symmetry. If I made this lambda theta m Planck, as it wants to be, because I mean, we haven't seen Lorentz breaking in our lives, then the pole becomes again a high energy pole. Okay, yeah, okay, there is a coupling, but I mean, this is if you take lambda theta to m Planck and little m to m Planck, which in the case of little m it's its natural value, in the case of lambda theta is experimentally what you want it to be, you get that the pole that you generated is precisely what you would expect from dimensional analysis without knowing anything about UV-IR mixing. It's a coupling square or a loop factor times n Planck squared. So initially, I have to say I was fascinated by this example. To me, what still remains fascinating is if you try to write the effective theory, then it will look very weird. You will not be able to integrate out the article. However, if I just think about this R pole a bit harder, I think there is nothing surprising about it. I mean, I don't think it's a genuine magical UV-IR mixing effect. It's really just the scale of Lorentz symmetry breaking. But this is my current understanding, which might change with time. What you have to take out of this brief explanation is that it's conceptually possible that maybe something like this happens for the Higgs mass, but the only model that comes even close to be concrete is a toy model, which breaks Lorentz invariance at order 1. And I would argue, at least with my current understanding, is stabilizing the light mass by breaking asymmetries of the Lorentz symmetry. So you start to see why I didn't devote too much time to these other ideas, because this is, if you want, the most concrete one in that set of 3 possibilities at the end of my list, and it's still very far from the mark, still very far from giving you an explanation for mx squared. Yes. Ah. To be honest, I haven't. So you mean this phi4 with the exponential? Yeah, to be honest, I haven't thought about it, but it does look a lot like a lattice model with some gauge fields on the links. I mean, this looks a lot. I mean, yeah, yeah, indeed, it looks like you are gauging the Lorentz symmetry and putting the Wilson line. So I bet that if we sit down for a couple of hours, we can figure it out. But I mean, I don't know off the top of my head. I mean, I don't think anyone has tried, at least as far as I know. Maybe they. I'm not. Yes. So yeah, I see what you're saying. But yeah, I don't have much more to say than what I already said. That I mean, I'm sure that you would see some sort of this transition when you're breaking the Lorentz symmetry, and then so above the scale, you see your normal 5⁴ on the lattice, and below the scale, maybe you start seeing this other pole. How to interpret it more precisely on the lattice, I don't know. It's a pity that we're already out of time, because the next thing I wanted to do was actually a model on the lattice that solves the problem. Like, okay, let me do it in 1 minute, okay? But also because, I mean, for you, I mean, Francesco, this is very well known, but for non-statistical people, it's less well known. So let me say I start with the easy model in 2D, okay? So in each lattice point, there is a spin that can be plus or minus 1. And my Hamiltonian is just a sum of nearest neighbors on this lattice. This is the sum of, this is my schematic way of writing a sum of nearest neighbors. What I wanted to do in great detail, but I want that time to do, is to show, which is a very, very well-known fact, that this model is dual to another model, which, okay, the most elementary way consists in building a second lattice at the center of the plaquettes. So now you have spins that live at the center. But so you're essentially mapping the model to itself, but in a very non-trivial way, because high temperatures are mapped to low temperatures. The two models are the same, so they both have only one critical point, and one can show that when you do this mapping of the free energies, the two critical points coincide. So when you do this symmetry transformation of moving this model into this other model, the only point that stays invariant is the critical point, the one at the phase transition. The phase transition is when you go from this Z2 symmetry, so this model has a Z2 symmetry, when it's linearly realized to non-linearly realized. This is the phase transition. And the only point of this transformation, going from one lattice to the other, leaves invariant is the point where you are on top of this phase transition, the critical temperature. Why is this interesting at all and relevant to the hierarchy problem? Well, the reason is that if you coarse grain this model, essentially if you integrate out high energy degrees of freedom that leave, let's say the typical scale of this model is the lattice spacing. So let's go at wavelengths that are much bigger than the lattice spacing. So that energy is much smaller than 1 over the lattice spacing. Near the phase transition, you can describe it as a phi square, phi to the 4 theory. And the mass of the scalar is 0 at the critical temperature. So we are seeing, so there is a symmetry in the discrete version of the story, which protects m equals 0, which is the symmetry is very non-trivial to see. If you look at the Lagrangian, you will never know it. And also, this very short description that I've given to you is kind of hiding a few things, because let's say the modern way of thinking about this duality or this symmetry is that you start with this model with the Z2, you gauge the Z2. So in reality, these spins don't have, even if the Hamiltonian looks like this, if you want to be really honest, the Hamiltonian on this other side looks like this. With this U, a Wilson line of the gauged Z2 symmetry. And I'm sorry that this is confusing, but I was planning to do it in half an hour. And so, okay, you have to ask what's happening to so how can a model with an honest Z2 symmetry map to a model that doesn't have the same symmetry? Because here the Z2 is trivial. So all the correlation functions have these U factors that also transform under the Z2, and under the Z2, they transform to themselves. So this is an honest symmetry that is transforming a correlation function to something different and telling you that they should be the same. On this side, everything goes to itself. And so the first thing you have to do is to understand where the Z2 went. And on this side, there is another Z2 that acts on objects of dimension 1. So there are strings in this theory that matter. But okay, this is all details, but this is the modern way of stating the story. And well, that's that's in 1 second what I wanted to tell you in a longer time, that in at least 2 dimensions, there is this intriguing symmetry that is totally non-trivial to see, even in the discrete case, that protects precisely the point that we're interested in. What I haven't had time to do yet is to work out precisely the transition to the continuum, so to see if this survives in any way. Maybe Pierfrancesco or other more experts than me know. I don't know yet, but it's kind of intriguing that there could be some form of non-trivial symmetry that we missed. There is a precise reason why this cannot be extended to 4D, but maybe something similar along these lines, not so simple, who knows? I don't know. So let me conclude with this. I'm already way over time. I will say only one more thing, which is that, well, the conclusion of these lectures is essentially that there is no conclusion. So I presented this long list of options, And today we have no idea what's the right answer. The goal of the lectures were to convince you that no matter what's the answer, we're going to learn something very new and deep about nature. Even more if it's one of these crazy things, of course. But even if we discover a symmetry or a multiverse, still we found something qualitatively new. I think that, I mean, I know of very few problems in theoretical physics that can promise you something like that. Maybe quantum gravity. In other cases, it's not at all guaranteed that we learn something qualitatively new about nature. Dark matter could be a boring particle like many others that we've seen already, for example. The strong CP problem can be solved by a simple action idea. Sure, there might be a new U1PQ symmetry, but not so different from other global symmetries that we've already seen. These, to me, the cosmological constant, the explosion mass, are by far two of the most interesting problems in theoretical physics for this reason. They're anchored at an energy scale that we can measure. So we might hope to learn something about them experimentally. And we have already learned a lot about them experimentally. I mean, we've killed all these explanations for the cosmological constant by just discovering the standard model. We are slowly disappearing a lot of explanation for the Higgs mass by measuring again the standard model. But at the same time, they force you to think about the UV, and even in very non-trivial ways. I mean, look at this. They might not be solutions yet, but they're certainly very different from what a particle physicist thinks about every day. So thanks for bearing with me all this time. And, I'm happy to answer any questions.
I just wanted to say that in principle it is possible to have 2 more hours next Friday. It's everything is free apparently. If you feel like and people feels like.
Well, let the people decide.
know.
I mean, I have 2 more hours, maybe even too much. I mean, I can probably do this in 1 hour, but I mean, there's no more than what I told you. I mean, what I would do is show you what's precisely this duality, constructing it, but you find it also in statistical mechanics textbooks. And okay, maybe I can add a few more comments on the work extra dimensions that we didn't have time to do.
There was Stefano which was asking something. Yeah. I don't know.
Well, let's say that the story is this one because you can show that this symmetry is a non-invertible symmetry. Well, there are 2 aspects. So first, the generalized symmetry number 1 is the Z2, the taxon strings. And then the second, let's say, non-trivial aspect of this symmetry is that you can think of this operation of going from one lattice to the other as a non-invertible symmetry. Yeah, so this is
Les gens viennent.
the short answer.
Very concrete questions. If we schedule a lecture on next Friday, who will participate?
Let's say 1 hour.
Watch it, but
Yeah, right. Yeah.
No, I'll watch. Well, I cannot guarantee because I have to check myself also. But 2 person.
Well, let's decide offline, and we can communicate via email to everyone.
I will. Okay. There is somebody who said I will. I will too. Okay, so we have 5 persons, more or less.
Not you. I mean, it's fine. I can.
Okay, so we will schedule. It's okay for you?
Sure. Yeah, let's do it.
Okay, so 1 more lecture on next Friday. I'll double check all the reservations and I send an email to everybody to confirm this. Huh?
Okay, technically on Friday I'm in the CNRS committee, but it always sends 1 day before. It never ended the last day, so I mean, like 99% I'm here.
Okay, so questions? There are questions?
I just went. So your last 2 points, they kind of suggest that one should look at maybe condensed matter physics. No, are there in the field of condensed matter cases, models where you have similar hierarchies and unexpected behaviors
Well,
that you know of or that people have looked at?
Okay, this is the most relevant one that I'm aware of. If let's say I broaden your question and let's say not only condensed matter but in general, maybe not in the same in 4 dimensions, then yes. I mean, so okay. First of all, I should say I'm not enough of an expert in condensed matter to tell you that this is the whole list. I can only tell you that this is the most pertinent. I mean, where you really can write a Lagrange and this is the same as the X, and you potentially see this symmetry maybe solving the problem. What I can add on top of this is maybe there are other instances that I don't know. Maybe the best example that I know of, which is more of a particle physics consideration rather than condensed matter, is that supersymmetry in 3D doesn't predict that fermions and scalars and bosons have the same mass. So maybe if we lived in 3D, supersymmetry could explain the cosmological constant. This is a paper by Witten of a while back. What else? I know a bunch of examples in 2 dimensions, which again, I wouldn't call condensed matter, where something unexpected happens. For example, there are theories of gravity in 2 dimensions where you can show rigorously, that all that quantum gravity does is, let's say, the S matrix of your theory without gravity is this. What quantum gravity does is that it dresses it with a phase and that's it. So it doesn't change the poles. So for example, this would be one example where gravity behaves as if it doesn't have a scale. It's a specific example in 2D, and the reason why I suspect it works is because gravitons are non-dynamical in 2D, so the only thing that gravity can do is iconal scattering, and in 4D, that's what iconal scattering does. So essentially scattering at large impact parameter where you can treat gravity as classical, effectively. Another interesting example in 2D, which is maybe more on the condensed matter side, more along these lines, is that if you put QCD in 1 plus 1, so when I say 2D, in this case I mean 1 time plus 1 space, you put QCD on 1 plus 1, I speak with adjoint fermions. I'm not 100% sure, but I can point you to the paper. But I'm pretty sure it's adjoint fermions. I mean, the part I'm not sure about is what's the representation of the fermions under the gauge group, but let's say adjoint. Then you can write down 2 operators that are both relevant. And if you calculate their RG equations, you will see that starting from your model, you will typically generate one, but this one doesn't generate the other. And if you look at the symmetries, it looks like a violation of naturalness because they respect the same symmetries. However, there is a non-invertible symmetry very similar to this one that explains why this is the case. So this is not really a hierarchy problem for a mass or a cosmological constant, but it's similar in spirit. So you have 2 operators that respect the same symmetry. You integrate out stuff and you see that one is generated and the other one is not. Even though based on the symmetries you can see from the Lagrangian, they should both exist. What else? I think this is more or less all I know. And if you are interested, I can give you the references. So the story of the specific model of gravity in 2D that only addresses the S matrix is a paper by Dubowski and collaborators that is in the notes. The story with the adjoint fermions in QCD in 2D is a paper by Zohar. I don't think it's already in the notes, but I will put it. And this one, this one is hinted at in many papers by Seiberg, by Clay Cordova, and other people. Also in the same paper by Zohar, where there is the other example. But it's never spelled out in great detail, or at least enough detail for a particle physicist like me. So I'm trying to write it down in the notes. What else? I mean, off the top of my head, I cannot think of other ideas, but typically, I mean, these unexpected occurrences happen lower dimensions, where physics is very different. I mean, and all these things have typically, in principle, reasons why you cannot extend them to 4 dimensions. Sometimes maybe it's unclear why, sometimes it's very clear why, but yeah, I mean, yes, so this is the list I'm aware of, and more in general, I think it's interesting, yeah, to think about condensed matter systems and see if they have something to teach us about the hierarchy problem.
Okay, thank you, Raphael.